Start.
Okay, hopefully it's audible.
Everyone, can you hear us?
I think it should be fine. Oh yeah, yeah. Okay, we got reactions. Okay, cool. I can start.
Okay, so yeah. The handout's not available? Yeah, it should be on Autolab. Okay. Okay, cool. So let's get started, everybody. So good afternoon, guys. And so far, congratulations. You've all been done with your homework part ones and part twos. So we're going to be starting with homework two, part one. And this is going to be talking about CNN, so convolutional neural networks. So, yep, these are the objectives of our homework. And sorry, yep. So this is similar. We have the same setup and submission code as we had similar to our homework ones. And we're going to be continuing with the same format. And this is basically the structure we have right now. So yeah, let me first kind of walk you through what a CNN is in general. So far you guys have been dealing with like multi-layer perceptrons and all. And even if we look at our first homework, we've kind of dealt with how MFCCs work in general. So far we kind of know, like, let's say we want to talk about like if we have like data about MFCCs and we want to represent data for like the word water. The way we do it right now is we kind of have like an entire layer of neurons, which is like a feed forward layer. And for every single time frame right now, we have like a neuron structured layer. But the thing is, what if we want to make this that's positional invariant? Let's say we want the word water to be somewhere else inside our MEL spectrogram data. And for this, every single time we'd be having to like make a different MLP with like different connections of the neurons. And practically, if you guys think about it, it doesn't really make sense. What if instead, or let me give you an example with like an image. So let's say we have like an image of a flower. If we have like an image of a normal flower, we would like, let's say the flower is in like the center of the image. The way we would deal with it is like we'd create like a neuron layer per every single pixel in that data, and we'd be able to like find the image of the flower. But let's say that same flower, if we moved it around here and there, like within the big image, then we'd have to create like a new MLP every single time. And honestly, this doesn't make sense. So the basic idea here is instead we could kind of do something what a CNN does, which is basically scanning through your entire data and is something like a movable MLP with shared parameters. So we just scan like the part of the image we want. So if you're looking at like a flower, right? We kind of create an MLP for that particular flower and we kind of scan it through your entire image. And in this way, you kind of look for what you're looking at. And the same thing with the word. Like let's say we want water in like a bunch of MEL spectrogram data. We just scan through. And if we find more water, we just say that it's a pass. So this is kind of a use case of how CNNs work in general. And yeah, the main structure of a CNN consists of the convolutional layer, and it consists of upsampling and downsampling. So when we're talking mainly about upsampling and downsampling, what we're trying to say is the movement of that particular scanner, right? It can kind of go with a stride. It could be jumping like multiple pixels or multiple time frames at a time. And this is something we set by the upsampling and downsampling. So if you guys go through the write-up, it kind of mentions in detail about how the whole concept of upsampling and downsampling works for either 1D structures and 2D structures. And yeah, so I'd encourage all of you to like go through the write-up once and read through all of these. The write-up is in like a lot of detail and it helps a lot. So yeah, go through the write-up and you will get to know about this. So now I think Thomas can talk about the conv layers and striding.
Okay, thank you, Pranit. And now I'll walk you through how the convolutional network works. So let me walk you through that basic concept. Now let's assume that we have a matrix called P1 and it has a certain cross shape. And we want to build a linear regressional model that detects this pattern. So the simplest way to build this would be to define another weight matrix, like matrix F that rewards, that gives high values for positions in the middle vertical and horizontal axes. So let's say if this weight matrix gives more value to the positions defined in this middle and horizontal axis, then it should be easy to define a regressional model that can detect this pattern. So this is the concept that we build up on in this convolutional layer and the whole homog to P1. So let's walk through each section step by step. We can start with conv1d stride 1. So here we're doing the same thing. So here we're trying to detect a pattern where the left position. So this matrix is trying to reward a pattern where the leftmost position is positive and the rightmost position is negative. So if you convolve this weight matrix over the input map, then you'll get positive values where these pattern exists and negative values where it doesn't. So this is like I said, this is the whole point of convolution. You just scan through the input map and try to find sections where those patterns happen. So if we're doing conv1d stride 1, we just take an element-wise multiplication of the input map. We convolve we call it a kernel, but this weight matrix over it, add the bias, and we should get values that tell us where these patterns are happening. So if we have multiple channels, we do the same thing. So in this case, we have 3 input channels, and for each input channel, we will have its respective kernel input, kernel channel. So let's say for this input channel, this is the respective kernel channel. So we will do an element-wise multiplication, and we can get those values that tell us if these patterns are detected there. So after taking the element-wise multiplication between the input channel of the input map and the kernel, we sum them up and then we can get a single scalar value. So yeah, if you read the write-up, it should give you more details about how this works, and we will cover this in the coming lectures as well. And for the backward operations, we're mostly doing the same thing. So the first thing we should consider when we're doing backward propagation is that the gradient has to be the same shape as the input. But when we're doing convolution, the size is going to decrease. So if you can see here, we started with 7, I guess, and then we ended up with 5. So to make up for that, we have to pad the gradient of the loss with respect to Z. So this is determined so you determine the size you need to pad by subtracting 1 from the size of the kernel. And yeah, so this should guide you enough so that you can get started on homog to P1. And what happens when it's 2D? So the same concept applies. We're just going to keep scanning. So let's say we have this weight matrix and input map over here. So we just keep convolving. So we take an element-wise multiplication of this weight matrix with the respective section and sum them up, add the bias, and you have your output for the first convolution step. And you keep doing that until you get all your output. And when we have 2 input channels, this is the same thing as the one we did for the 1D convolution layer. So here we have 2 input channels, and for each input channel, we're going to have its respective kernel channel. So here we have 2 input channels. here we also have two input channels. And in this example, we have three kernels. So the main thing you have to keep in mind is the number of input channels tells you the number of kernel channels you need. And the number of output channels, in this case, 3, tells you what the size of your kernel is going to be. What the size of your output is going to be, sorry. And so far, we've been doing convolution with stride 1, which is we're just taking one step at a time. So, but what if you want to take multiple steps at a time? In this case, you have to do the convolution and apply downsampling. So in this case, when we mean by downsampling, you just drop a few elements. So if k is 1, it means that you drop every other element. So for instance, here, we're just dropping every other element. So we just keep 3 and then -5, and the pattern keeps going in each direction. And another section you will encounter on this homework is transpose convolution. So if we keep doing this over multiple layers, then at some point our output is going to keep decreasing, and we won't have a lot of data to work with. So we have to upsample the data before passing it to the next layer. That's what convolutional transpose convolution does. So we first upsample and then we do the stride. That's the only difference. That's the only difference here. So all this is going to be built up on the previous sections you have implemented so far. So you've already implemented the com1d stride at this point, and you've done the upsampling as well. So this is what you're going to combine for this section of the homework. And another section you'll encounter in this homework is pooling. So here you're trying to, let's say each kernel is trying to detect a pattern, right? So let's say if a certain pattern exists in a certain region, this is how you can figure out if that pattern exists or not. Let's say this kernel is trying to detect if there's a certain age or a certain color in your input map. So you just take a max pooling to determine if that pattern exists over a certain region. So all you do here is just take the maximum value and pass it to the output. So here our maximum value is 3. It doesn't have any parameters. It just takes the maximum value. If it's max pooling, otherwise mean pooling, where you take the mean of all the values. Next up, Akshara will take you through the flatten layer and the scanning MLPs.
Okay, so hi, I'll be taking over the leftover portions for the write-up. So in part 7, you'd be working in flattened on pi. So basically, this layer is often used between convolution and linear layers. So the main thing I would say is to focus on the reshaping. So the forward only part is reshape only, while backward you need to reshape the gradients back to the exact original input shape. So just look out for that and follow the components which are given over here. And the next part, mostly, I feel like that's the most important section, and we would tend to spend more time in this section, which is converting scanning MLPs to CNNs. So in the case of 8.1, this uses a toy example to explain the whole setup. And I'm not going to go into details, but this I feel like this part of the write-up is really important. So please go through all the details given over here. And one of the key points is that for 8.2, that is CNN as a simple scanning MLP, this section is relatively hard to implement if you don't really go through the write-up. So please know that the TAs will not help you debug your code until we have seen your attempt to draw it on a diagram. So on all Piazza posts, we request that you start, like, if there are any questions regarding this section, we want you to start with the phrase that you have read section 8.1 and then go on with your queries regarding this section. And same applies for 8.3 as well. So for the main things that you'd have to perhaps um, look for is just make sure that all your environment is consistent with the homework one environment, and what you're implementing is kind of consistent with that. But if I were to go into detail for this, it would be a little long. So just please go through these sections on your own. Yeah, thank you.
Okay, so they can see everything.
Share support.
Didn't matter.
No, hey, project. Hello, everyone. My name is Yapso. So we're going to be presenting about the Homework 2P2 Bootcamp. To begin, first, it's good to begin with a reflection of the previous homework. Try to think of anything that was challenging, but you figured it out. Is there anyone who wants to share any challenges? If not, you can just think about it. Same thing, which strategies or resources that helped you the most, what you do differently, if you could start over. These are important things, and you don't want to make the same mistake again. So the things you figured out, great job. What strategies you used, remember that to use that in homework 2 as well. And what you would do different, also remember that for homework 2P2. Now, before we begin, let's just a couple of notes. Homework 2P2 will be significantly more time consuming than homework 1P2. This will be because the models will be harder to develop. They're going to take more time to train and more time to converge as well. The notebook won't also have as much handholding. You're going to fill out more things, more cells to write, and you're going to, of course, train the model from scratch as well. So please start early, and also strategize with your study team, because there's going to be more architectures to implement, more training strategies and parameters to test. So it's good to start early, use what you learned, and try to meet up with your study team and classify the experiments, so you'll have enough time to reach the high cutoff. Okay, so the goal of this bootcamp is to help you get started with homework 2P2. You're going to be learning about convolutions and salients in the coming weeks, but this bootcamp will help you get started with the homework. We'll be going over the problem statement, workflow. We'll tell you about the data loading and pre-processing, how to build the model, different training, modeling, testing, and calculus submissions as well, and the different loss functions you'll be using for this task. Finally, we'll take about the questions. So the problem statement, unlike homework 1, in this homework, you're going to have 2 tasks, but even though it's 2 tasks, there's going to be 1 model and 1 submission. The
Hey,
tasks,
quick thing. Are you sharing these
yeah,
slides?
yeah, it's not visible.
Not on my end. Let's see.
Oh, my bad. What about now?
Yeah, I can see it now. Thank you. I'm sorry.
Yeah.
Okay, so let's just repeat the problem part. So in homework 2P2, there's going to be two tasks, even though there's going to be one model and one submission. The tasks are face classification and face verification. And this might seem a little confusing. So let's define what these tasks are. So face classification means provided an image or a photograph of someone, you're trying to identify who that person is. So in this example, you'll be given this image, you're going to output Satya, you're going to get an input of maybe this person, and you're going to get Mark, and you get an image of someone, and you're trying to identify who that is by basically classifying them. And if you see an image you haven't seen before, you won't be able to classify it. So you're still going to classify it to that person, but it's not going to be the right person because you're just going to be classifying it to what you believe it is. So it has a couple of drawbacks. We'll talk about that, but it still can be used in a bunch of systems. For instance, like an attendance system where you have an attendance for a class, you have the photograph of everyone and their names, and no new person won't be added to a class. Such type of model would work for that. The second task is face verification. Here, the task is slightly different, where you're going to have two images, and you're trying to find out if those images represent the same person or different person. In this example, you'll see two images, and you're basically trying to see, are these people the same people? So is it satire or no satire? Or do they match or do they not match? This is similar to what might be using in your smartphone to unlock it. So when you set up your smartphone, you basically register an image of yourself. And anytime you try to open your phone, it takes the image of what's available in the camera and tries to match it to what's already stored. So this is basically how face verification works. But they do have also similarities in how they work, and we'll go deeper into that. But what happens in this like black box system? The input goes and it enters a feature extractor. This will be your CNN or CNN variant. We'll talk more about that. And this will output a face embedding. Face embedding is basically the representation of your face in the embedding space. Think of it representing different features or different aspects of your face. It can be your skin color, skin tone. It can be the shape of your eyes, shape of your nose, etc. This all you'll try to represent this, and this will go into a face classification model that will take the face embedding as an input and try to classify it, try to get the class, or in this case, the ID or the personality of the face. But face classification is close to a set of predefined identities. So if you want to add a new identity, this will require you to retrain the model. So this makes sense if you already know all possible peoples in your data sets and you want the model to classify it to one of those identities. The second option being the face verification is not limited to the training identities, and the goal is slightly different. The goal is to generate a good representation or good face embedding that's rich enough so that if you compare it to another embedding, those embeddings are detailed enough, you can compare them and try to find if they are the same person. So that's the goal. You get good embeddings, compare them, they are the right person or not the right person. And this can also work for identities or faces you haven't seen in your training as well. Okay, this model, I hope it's visible. This is kind of represents what you're going to be doing in this assignment. So here you're going to be loading your data, data transformation, augmentation, all this will be explained after this. And then here will be your feature extraction CNA model. And this will output a face embedding, which I talked about. And here was where the tasks separate. You got your classification and your verification. So in classification, a single image enters, it will be projected, and then enters a softmax, which you can use to assign probability and label your data. And this will give you a label for your identities. And here you can calculate the accuracy, which you can use to save the model. But of course, you will use cross entropy as your loss. But in addition to that, you can also use additional losses, margin-based and feature-based losses. This will also be explained after this. And you can combine these losses, assign them different weights, so you can combine them in different manners. And this will be the loss you use to train your model. And training will only be done using the classification task. That's one thing to note as well. And if you can produce a rich enough embedding, you can go to the next task of verification. Here, your input will be a pair of images. You have two images, two face embeddings. And once you have these two face embeddings, you can just calculate a similarity score between them. You can use cosine similarity, and you can use this similarity as a way to identify if these people represent the same person or not. Here, the metric you'll be using is equal error rate. This will also be explained. And this metric is the one you're going to be using to save your models. This will also be the the metric you're going to be using to test your models and make your Kaggle submission as well. Is everything clear here? Okay, great. Okay, let's go over the ideal workflow. So you want to download the notebooks and your write-ups, go over each of them, read them, and make sure everything's clear. Complete all the to-dos similar to homework 1, and try to reach the low cutoff and submit that to Kaggle. This is again similar to the first homework. An important update. So there will no longer be checkpoint notebooks. In homework 1, we provided with checkpoint notebooks where you guys answered a bunch of questions, put in your Kaggle username and generated submission file and submitted this to AutoLab. This was kind of confusing to a lot of people. So we've transitioned back to just using homework quizzes on Canvas. So for this homework, there's going to be a homework quiz on Canvas. And you basically have to finish that before the early submission deadline, which is February 20, and you want to finish that before everything. But so no longer submission of checkpoint notebooks to AutoLab still, but make sure to finish it in Canva. Now, even though the early submission deadline is February 20, and that's like 2 weeks away, you want to start earlier because there's going to be a lot of tests and a lot of experiments you have to test before you reach the high cutoff. So divide the experiments among your study group, try to find out which models work, and try to test as much as possible to reach the high cutoff. And that will be your final step. Okay, I think that's it. Manchu will talk about data loading and pre-processing.
Okay. Now for the dataset and data loader, which you have experienced in homework 1P2 before, where you only have one dataset. But in this homework, we have two datasets, face classification dataset and face verification dataset. So in the classification dataset class, we have train, while, and test set. And in verification dataset, we only have validation and test set. So we expect that you can first train your model on classification dataset, as we mentioned before, and then fine-tune your model on verification dataset. And also, again, the key difference between these two datasets is that in the classification dataset, each sample is an image with its label. But in the face verification dataset, each sample is a pair of two images or two faces and its corresponding labels, seeing that whether these two images or two faces are from the same person or not. And also, as you know, for each dataset, we have a corresponding data loader to help us loading the data in batches or handle other settings, for example, whether to shuffle the data or not. It should be very familiar with you in homework 1P2. So just a quick recap. Then move on to the image augmentations. You have encountered some augmentation techniques in homework 1P2. Remember, you do time frequency masking in homework 1P2. And here, since you're working with images, so actually you have more techniques to play with. Let's start with the first question. Why do we need to do the augmentation on the images before we training the model? So in general, when you do the augmentation, you introduce more variance to your data set. It's not just you trying to create a completely new data, but it's that you are trying to make your original image look a bit different from before. So in this sense, it feels like you have expanded your data. It's just that you're trying to use an effective way to add a richer distribution of our data sample. So by doing this, your model will not just see one version of a same image. It will see so many different versions of the same face. And so as a result, it will help prevent the overfit of your model because your model is just trying to memorize the faces with exact the same form. It will learn and see so many different forms of same face so that it will learn how to recognize the same face under so many different variations. And also that's why it will usually give your model better performance in the generalization part. For example, your model can learn how to recognize your face, no matter your face is in the front-facing view or is in the side view.
So as a result, the augmentation techniques is super simple and powerful tools that can help you to improve your model generalization performance. So you may need to try in this homework. Here are some sample augmentations that you can consider to try. For example, random crop. This is trying to crop the images at different position. And random rotation is rotate your picture a little bit because your face in real life will usually come into different angles. And for the flips, we usually will consider horizontal flips and vertical flips. But just a note, in this homework, in this face-related task, usually horizontal flip is fine, but vertical flip is not really make sense for these face tasks because like in real life, it's not really common that you will see some people with their face upside down, right? Unless you're doing some weird experiment or some special stunt. Then here's a color jitter. It can change your picture's hue, contrast, and brightness so that the model to learn how to handle different lighting conditions. And a random perspective is trying to distort your image a little bit to simulate different viewpoint of your face. Here are some tips for you when you implement the augmentation techniques in your notebook. So first, please consider to do the normalization after you applying some augmentation techniques. Because some of the augmentation techniques can do overlay job. That means it maybe will push your image into some extreme cases. And it's very easy for your model to be biased by these extreme cases. That's not what we want. So we usually will do normalization after the augmentation techniques because it essentially evens things out. And it will avoid your model to be biased by one or two, some extreme cases by that. So it will make your model training process more stable. And second, please also remember to convert your image into the tensor type. Because when you're doing training, what you load is not the raw image, it's the tensor type. Here is a typical transform pipeline that you may see in your notebook. So here we have this compose function, and within this compose function, we can stack different augmentation techniques here, and you can add more at here and try different combination with different augmentation techniques. But also remember to do the tensors, convert the image into tensors and do the normalization afterwards. Here is some images after applying augmentations. It's how the augmentations applied to image would look like. So you can see here some grayscale, and you do some color jitter, and with some different viewpoint here. But let's look at the first row of these pictures. Do anyone know what augmentation techniques we are doing here? Do anyone want to try? Okay, so you might think that the first row might not look like some simple augmentation techniques that we have introduced before. It don't look like a same person. It looks like more like a combination of two different persons' face. So this is a technique called cut mix. It works out by cutting out one image and paste into another image. For example, cut out my face and paste it into maybe Akshara's face, something like that. So you might wondering, why do we need this technique? Will this technique distort our data set? Because it's just feel like you are just combined two different people. But just a note, like in this process, when you combine these two different people's images, your label will also be mixed proportionally so that it will indicate which area belong to which people. And I can share my take on this, like why this cut mix augmentation technique would helpful in this task. So I think like if your model always sees some single face or some complete whole face at each time, there might be some cases that your model maybe only focus on some obvious or very simpler features. But when you want to transfer your model to some harder scenario, your model may be failed because the feature it's trying to learn is not enough to generalize. For example, if your model always sees the whole face of the rabbit, even if you can add some simpler augmentation, like you can just turn the face, have different viewpoint of the face, there might be some cases that your model maybe think the long ear is enough to recognize a rabbit face. So it might be think like the long ear is enough to equal to rabbit face. But if you want to generalize to some harder scenario, like if the data sets have some other animals with long ears, the model may be failed because it only tried to grasp some very simple features from when the model doing the training. Like this, how to separate them. So when we do the cut mix, but let's record in real life. Like even if we block out the long ears of the rabbit face, sometimes we still can recognize, oh, this face is from rabbit, right? Because rabbit usually have other features like their eye color, their fur texture, something like that. So my personal taking on cut mix is like one way is trying to give your model a harder scenario. It block out some of the features and force your model to try to learn some other features or some other not super obvious features or detailed features, and trying to let your model trying to based on all of these features and try to recognize your face. So that's why when your model generalize to some other transfer to some other task, it will give you your model will also do better. And also, like in our real life, our face will sometimes be blocked by some objects or be overlaid by some other people's face. For example, in this picture and in the group photo. It's just very similar like what happened in the cut mix picture you see before, right? Your face may sometimes be overlaid by some other people's face. So I think cut mix is just trying to give your model a harder scenario so that your model have to learn as many as possible the features and trying to rely on a wider range of features to try to recognize your face. And also there's other technique called mix-up. It also have similar idea, but it's trying to merge or combine the pictures in the pixel level. So you can see after the merging, the merging will look more smoother than the cut mix. It do not have the clear line between the two pictures. You can try in your homework because from our experience and observations, usually doing cut mix and mix up will give you some surprising results, like in your Kaggle computations. And also just a note, for mix up and cut mix, when you implement in your notebook, it's more difficult than the augmentation techniques we have introduced before. It cannot just simply implement in the compose function as we shown before. You need to manually implement them either in the collate function in the data loader or before the training loop. And this slide just want to emphasize that the augmentation technique is super, super important in this homework. So if your data in your data set is always look like these 4 pictures on the slides, it's very clear. And it's always like whole face, and it only have one exact form. When your model generalize to some different task, it will fail. So please try to do some augmentation and play with some augmentation combinations in this homework. Okay, that's all for my part. And then I will pass on to Yapsara for the model introduction.
Okay. Hi again. Okay, so a little bit of this is work covered in the homework 2P1 team. They talked about this as well. But what's the real reason why we can't just use a linear layer, the one you use like homework 1? Just create an MLP and just run it through it. So the first reason is there's going to be a lot of neurons. So let's say this image has a 1000 times 1000 pixels. And let's say each pixels, you're going to be an input node, you're going to be sending toward your hidden layer, which also has like a million hidden layer. That's like, so when we flatten this out, 1000 times 1000 is going to be a million input nodes, and then another a million hidden neurons. So this will be 10 to the power of 12 trainable parameters in only one layer. And this is like a lot of parameters. And it doesn't also generalize so well for shift invariance. This is like what Pranis mentioned, where the flowers located at different places. And since salience, they work by convolving, that means they scan your entire image. They can detect it even regardless of the position. And that's why we need CNNs. And like this is where CNNs comes. They convolve through your entire input, they minimize it until you get your final class. And basically this was all explained. Is this unclear to anyone? Okay, please. Yeah. So the kernels will be your parameters. They are shared. So the kernels you're going to be convolving, right? And they're going to be the ones that are going to learning, and they can be across channels as well. So for instance, let's say you have a colored image. It's like RGB, red, blue, and green. You're going to have a kernel in each layer, in each channel, and it's going to be the one and that will be the parameters that's going to be learned. So that's basically be the weight in CNNs. Okay, and any questions? Okay. So why do we use CNNs? They're really good at capturing spatial patterns. That means if you're looking for maybe a petal in a flower, or you're looking for lines, circles, earlier layers of the CNN will capture maybe lines, circle, and stuff like that. Later layers might capture your eye, or they might capture nodes and stuff like that. So they're really good with working with spatial patterns, good at feature detection as well. They share parameters. So instead of learning each parameter for each node, that kernel that's going to be convolving, that will be shared, and that means less parameters you're going to train. Translation invariance, like we mentioned with the flower, and computational efficiency. We sometimes perform pooling, max pooling, min pooling. You learn all about this. They basically will decrease your kind of like your image to a smaller matrix, so that you won't spend as much time. And we'll actually cover a little about that when we discuss about Resonate. But is this enough, like for your homework? Sadly, no. And you're going to need more complex architecture. This might even require to go over some papers, read over them, because there's going to be different types of architectures. Common examples here are Resonate, AC Resonate, ConvNext, and a lot more. So if you're looking for architecture, feel free to search for papers and try to find it. But remember, attention isn't allowed, recurrence only CNNs. And if you feel like something is unclear, or if you're not sure, ask Compiazza or attend Officer. Any of those work. Now, when trying to implement a specific concept, there are two tips. Try to identify what type of block they're using and what's their unique aspect. These are two things to see. We're going to see that as well. So let's talk about Resonate. Maybe a couple of you have implemented residual connections, maybe in your homework 1. If not, we're going to talk about that as well. So Resonates were introduced in this paper, I think 2015. And for instance, if you're going over this paper, you can notice the things that I mentioned earlier. What are the blocks and what are the main aspects? In Resonate, the blocks are basic blocks and bottleneck blocks, depending on what type of Resonate you use. I'll explain about that. And the main aspect is residual connections. So residual connections can be applied not only to a CNN, basically you can add them to any type of neural network you're using. You might have applied it to your linear layer in homework 1 as well. So normally when you iterate sequentially, an input enters a layer, you do all the computations, and it outputs a value in value. So an x goes in, and f of x leaves. But technically, you're learning the change. But what if you can instead learn the change? So f of x is just x plus a different value, right? So instead of learning how x transitions, can we learn the change? So instead of learning what f of x is, can we learn f of x that you can add to your initial value, and you can still get the value you want? And this is how residual connections work. It basically works by skipping a couple of layers, and the couple of layers you skip will learn the difference or the change. And this is very important because when you're working with very deep networks, we see a lot of issues such as exploding gradient or vanishing gradient, where basically where you're returning your gradient, it might decrease to a value so little that it's pretty much inconsequential, or it might increase to a very large value, stuff like that. So residual connections avoid this, and empirical experiments have shown that that they perform better. That models that use residual connections perform better than those that don't. So please keep this in mind when you're implementing this, especially if you're going to have a lot of layers. This is very important. Is it clear about residual connections? Okay, so basically what I told you is like you try to find out f of x. But another thing to note is f of x might not be the same shape as the initial inputs. So you're trying to do element-wise addition, but they might not be the same shape. You can't simply add them. So you might need to perform mapping of your initial x. This is something you want to note. Or you might even map out f of x. So that you can't simply add them sometimes. So keep in mind the shape whenever you're trying to construct this. And then after adding, oftentimes an activation function, ReLU in the official paper is applied. So I just told you that there's two types of blocks that's oftentimes used in ResNet. The first one is basic block. Basic block is an input, it's basically given an input. A 3x3 filter is used for normal convolution, then a ReLU, then after that another 3x3 convolution, and the output will, I forgot about the batch normalization. So after the convolution, there's going to be a batch normalization, then a new ReLU, then another 3x3 convolution, then batch normalization, then this will be summed up with your initial input or x, and then this will enter the ReLU again. Okay, please.
Looking at 64, I'm guessing that means like dimension element or something about size.
Yeah.
After each convolution, doesn't the dimension of the image or whatever get smaller? So why is the dimension element the same?
So this is technically, so again, you learn more about channels. So this is kind of, you're going to have multiple channels, right? So let's say channels are basically different representation of your image. Like I said, if your image maybe an RGB, it might have three channels, one that represents the red, one that represents the green, and one that represents the blue. So after you iterate it, if you have 64 kernels, or 64 filters, and each of these filters does a convolution, it will have its own channel output as well. So as long as your number of the number of your channel output will be the same as the number of your the number of kernels used to do the convolution. Okay, this might be a little confusing, but again, once you attend the class, this will also be more clear. But as long as the number of your filters will decide the number of your channel output, because each filter will kind of be looking for something, and that will be what the channel output represents. So it will be different representation of the same image based on the each filter it's converged. So if it has 64 filters, there's going to be 64 channels of that representation. Is it clear? Okay, so basically, as long as you keep it in mind, it is. We'll actually see that now bottleneck is interesting. So what happens is when you have a large amount of layers, it can be computationally like really expensive to do a convolution. So if you have like 256 channels, you can't do a convolution operation in all of them. It can get expensive one. So here, what we do is the first step of like bottleneck is a pointwise convolution reducing the channel. So point one convolution. So instead of having like a matrix that you convolve through it, imagine having just a 1 times 1. That will be your kernel, and you're going to be convolving through that. But here you're going to decrease the size. So your channel, your input channel might be 256, but when it comes to your number of filters, that will just be maybe 64. So your output will be 64. So you, for instance, you say that it should decrease. Well, here, since the output is 64, it's kind of decreasing. And this will be, and here you'll do the majority part of the computation where you convolve using a 3 times 3, and then you return it back to the 256 here. And since 256, they're, if considering they're the same type of shape, if they have the same type of shape, you can sum it up and do a real. So maybe to repeat what I said. So in basic block, you have your input, you do a 3 times 3 convolution, then this will enter a batch normalization, a ReLU activation will be applied, and then you'll again repeat a 3 times 3 convolution, batch normalization. It will be summed up with the original input, then this will enter the ReLU. In basic block, you're going to reduce the number of channels using the first layer. This will be a pointwise or 1 times 1. Pointwise convolution is basically, it doesn't look to its neighbors, so it doesn't have any context from its neighbors. It's just one 1 times 1 size kernel that's going to be iterating. The main job of it here is it does get properties across channel, but it also reduces the channel. And then you do the main part of the computation, where a 3 times 3 regular convolution, while it's maintaining your channel at 64. Batch normalization and ReLU will be applied here as well. 3 times 3 convolution, then a batch normalization and ReLU, and then you return back by using a 256 filters as well. And then this will again be a pointwise convolution, and this will give you an output which you can, after batch normalization, which you can sum with your input and put into a ReLU. I know this sounds really confusing. Any questions, please feel free. No? Okay. Okay, let's go maybe with a sample code. This might make it simpler. One thing to note, this is not the code for this homework 2, so it's not a CNN, it's just for the linear layer. So don't get confused on this one, or try it on there, it probably won't work. So a basic block, like we said, we have NH and H here, we're gonna keep it up. We're gonna keep what we had. So we have this linear layer, batch normalization, and ReLU. So we have that the initial input. We store this initial input because we're going to sum it up later. Remember this part using R0, right? So your initial input will go through the linear layer, then a batch normalization, ReLU, then it will enter another linear layer, another batch normalization. Then this batch normalized will be summed with the initial input, and this will enter the ReLU. If this was a convolution, it won't be a linear layer, it will be a convolution with a 3 times 3 kernel. And by the way, this is the original paper from RaisNet. You don't have to follow this, like just do normalization before the convolution as well. You can experiment with different stuff. This is just the original paper. Now, when we go to the bottleneck layer, so one thing to note, we're kind of imagining that the input is the size, already the size we want. So in this example, we are not reducing the number of channels. So we have a residual network here. We have our linear layers and the batch normalization and the ReLU, same thing like that. Now, when we store here, we put it through the residual linear layer here, because again, we are assuming that it's already been reduced when it comes to this input. So later on, when we sum it up, since the last layer is going to increase the number of channels, we're going to try to match the shape to the output shape, since we're going to be adding it. And that's the kind of the point of the residual connection. And then it goes through the entire step where it enters the linear layer, enters the batch normalization, ReLU, another linear layer, batch normalization, ReLU, same thing. And then you sum it up in the end, and that will go to your ReLU, and that will be your final output. And this is a single residual block. You're going to layer multiple of this up. Let's look at an example. So there are different types of RaisNet 18, 34, 50, 100, something. So there are a lot of them. You want to also see before you implement any of them, don't forget the parameter count, 30 million. You want to keep an eye on that as well. So here you have basically this is called the stem, where the main goal of this is just going to be a large convolution. It does average, it does max pooling. So you're trying to decrease the size, trying to get only the more important information out of it. So an initial convolution, these are kind of like stages, and each stage will have a block, and these blocks can be repeated. And inside these blocks, there's going to be convolution layers, there's going to be batch normalization, and in each convolution layer is going to be batch normalization, ReLU, etc., like we explained. One thing maybe you might have noticed this. So the 18 layer, RaisNet 18 and 34, they use the residual block of a 3 times 3, 3 times 3 convolution. This shows that both of this, they use the basic block. So they use two 3 times 3 convolutions. While the 50 layer, it first has a 1 times 1 convolution, a 3 times 3 convolution, and then a 1 times 1 convolution again. This indicates the bottleneck residual block that we mentioned. So the larger 50 layer one, they use the bottleneck blocks because you want to reduce the amount of computation you do. Finally, you're going to use an average pool, and then you'll use 1,000 diameter. Again, it depends, but on which application you're going to be using, you're going to use a final classifier model, and then a softmax, and you get your output. So this is basically what the resonate architecture looks like. Sure.
Or doing what, like times 2, the times 3, what do those mean?
Okay. So yeah, I don't think I explained that part. So this is one residual block, right? Only this one, right? So inside the residual block, inside this residual block, there's going to be a convolution using a 3 times 3 kernel that they talked about. So this will be the convolution one. And the number of kernels you use, in this case, is going to be 64. That will determine how much output you have on the channel side. So for instance, the input channel might be, I mean, this will be 64 because of this, like this can be anything, the input channels. And then the output will be 64 channels, and the next output will also be 64 channels. So think of channels like layers. So you have images, there's going to be layers of those images. So your input will be how much copy, it doesn't have to be copy, but representation of that images. That will represent the channels. So when you're convolving through that, the number of each of those convolutions is going to have one channel. So if you have multiple filters, those will output the final. So imagine like, just to start with, yeah. Okay, so think about this. Like you're trying to detect an image, and that image initially has 3 channels. And then let's say you have 5 kernels. The first kernel just is trying to detect eyes. The second kernel tries to detect nose. The third one tries to detect your lips, and so on. So, and then the first channel that only detects eyes is convolving through this image, and it will have its representation, but its representation is a representation where it's just looking for eyes. Yeah, it's going to have, yeah. And then it's going to have, and that will be one representation. And the second one is looking for a nose, and that will be another channel. The mouth will be a third one, and ear might be a fourth. So now you have 4 channels. Initially you had 3, now you have 4 channels, right? Exactly, yeah. That will be the output will actually decide the number of channels will decide your output. And then now once you have that output, the next layer might maybe looking at the position of the eyes. So the next layer will trying to look where there's an eye and an eye here. So it's taking your new kernel as an input, and it will have an output that will depend on the numbers of filters that's available on that layer. So in this layer, it has 3 times 3 kernel, and there's going to be 64 of those kernels.
You will then get a block that is 64 channels, right?
Yeah, for each. Yeah.
Yeah, I didn't realize.
Each will produce. And the times 2, so basically in the 18 layer, in the first part, in the first stage, you have 2 of these residual blocks. So, and the 34 layers will have 3 of these residual blocks, and the third layer of the 50 will have 3 of the bottleneck blocks. And this is basically what it defines. And even like if you see the image that's on the far left, you will see that how it skips. So again, same thing. Important part about residual connections, it sums up with the initial input. So it does the iteration, sums it up with the original input, adds the iteration. So this is what it looks like. It's going to be jumping and jumping and jumping. Sounds good, right? Yeah, please. Okay, so when you do basic convolution, and we also even explained that, so you do across basically across your neighbors, but across layers as well. Yeah, it will have, and those will be all learnable parameters, basically. Exactly. Okay. Again, it will get clearer once, especially after you have attended the lectures, and it will be much, much clearer. But this is more to give you an overview, especially to start the assignments. Okay, so general architecture overflow, like I mentioned. So think, especially when it comes to like RaisNet and you're implementing these networks, first think of them as stages. And each of the stages will have blocks, and these blocks will have CNN layers, batch normalization, and redos. So here, this will be a stage, and each will have blocks. The blocks can be bottleneck blocks or basic blocks. And inside these blocks, there's going to be convolution networks, batch normalization layers, reloose, or whatever activation used, etc. So that's kind of like try to, instead of just imagining it as conventional layer, try to first give them like a hierarchy, and that will make it easier to understand. And yeah, so this will be for understanding them. Yeah, and like the change of the blocks is like the number of the channels is something you also want to keep an eye on. And this kind of what it looks like. You have the initial part where you have the raw image and you're trying to change it to something that's understandable. Then you'll have multiple stages and multiple blocks of your input. And finally, you'll have a classification layer. You might use a linear projection, and that classification layer, in the end, it always be a softmax to output the probability in this case. Okay, a couple of summary. A normal convolution mixes both from like different channels and across spatial locations. So it's like a matrix. It's combining information from all around its neighbors, but also across channels. That's something to keep an eye on. There's point-wise convolution where you don't look at your neighbor. There's depth-wise convolution where you don't look across channel, you're just going forward. But a normal convolution that you oftentimes use, it combines both from the channel and from spatial location. To convert papers, whenever you read papers and trying to implement something, try to understand what the block looks like. Is it a basic block? Is it a bottleneck block? Or is it some type of different block? And then what makes this paper different? Like, is it the architecture? Does it add something new? Try to look for both two things. Residual connection provides another path for data to reach it. It's not straightforward. You first try to look at the change and add it. And also when you're looking for new papers, try to avoid attention and recurrence. And also the parameter limit is for this homework is 30 million. So don't pass that mark as well. Any questions in the model section? Okay, I think done for this part. Puru will tell you about training, monitoring, and testing.
Hello, everyone. Can you hear me?
Okay, I think you're on. We can hear you only from the.
Let me test.
There, mic. Huh? I'm sorry.
Sorry, do you have to route
Okay.
the audio?
Oh,
Hi, Pru.
can you try?
Hey, can you hear me?
Can you hear?
Nobody
Oh,
can hear me?
wait. Is it on?
I think the people remote can hear me.
Yeah,
I think
we
that's.
can.
Wait, so should can I start?
Oh, wait. I think it's better if you share your own, so that's.
Sounds good. I can do that. Give me 1 second. Sorry, guys. I was the only remote presenter, so there was bound to be some issues, but we will get through it. Can you guys see my screen?
Yeah.
Awesome. Awesome. Thank you. All right. So I will be covering the training, monitoring, and testing part of this assignment. You definitely did encounter some aspects of this in homework one, part two, but given the differences between the two assignments, it is important to revisit this with the lens of how it would change for homework two, P2. Also, I know that it might feel like we are bombarding you right now with a lot of information, and that's fine. That's a completely normal thing to feel. Our goal here is to so right now, just take what you can as a high level, but our goal here is to hopefully serve as a reference that you can come back to in the future as you've gathered more context through the lectures and doing the assignment, right? So before we get into training, monitoring, and testing, it's important to kind of get a high level intuition on what you're being evaluated on in this assignment. Right. So before we get to that, let's first revisit the concept of a binary classifier. Right. So what is a binary classifier? It is a model that simply predicts one of two classes. For example, spam, not spam, fraud, something is a fraud or something is legit, whatever the notion of fraud or legit is for your particular task. Uh, and in our case, we might what we would be binarily classifying is if two faces are the same or if they are different. And so typically you would assign something either a label of 0 or 1 based on some convention. And you would do this by having a model that assigns a score and then setting a threshold. And so any score that passes that threshold will be assigned a label, and anything that is below that threshold is assigned the opposite label. Right. So this is in our setting, we'd be taking in pictures of images of faces. We would be passing it through some awesome model that you have coded up, and your output of this model would be a feature embedding or a face embedding, which is essentially a high dimensional vector that is representative of a face, right? And the goal of our model is to kind of emphasize the discriminative abilities of these embeddings to ensure that you're able to create a model that outputs these high dimensional vectors that are highly discriminative in nature. For example, if given two different images of my face, they're able to say that it belongs to the same person. Whereas if when comparing mine and say Mengchun's face, the model is we are appropriately able to determine that these two images belong to different people, right? So some confusion matrix basics, which it'll become more evident why we are talking about these concepts. So true positive is a sample that is a positive sample that is also correctly predicted as positive. A true negative sample is a positive sample that got incorrectly predicted as negative, right? False positive is again a sample that got predicted as positive but is actually negative, and then false negative is a sample that got predicted as negative but is actually positive. So, why is accuracy not? So, in your homework one, part two, you guys used accuracy as the metric of evaluation, but why is it not good for our task, right? So, accuracy again is a sum of like the number of positive classifications divided by the total number of samples. So that would be the number of true positives, and that would be the sum of true positives and true negatives divided by the total number of samples. And this can be very misleading for imbalanced data because we are not actually taking into account the types of errors we're making. So, for example, for a fraud detection task, if the data set we have consists of 99% of non-fraud data sets, if we had a model that always predicted non-fraud for every sample instance, we are getting 99% accuracy. But that is not what we care about. We care about how the model behaves. We also care about how the model behaves in that 1% instance of fraud instances, where how does it perform? How well is it able to classify those as positive or negative instances? We care about that as well. So there's this notion of like some mistakes being worse than others, right? So, here are the error rates that actually matter for this assignment. We have the false positive rate, which is how often we falsely raise an alarm, which is the formula is right up there. And then we have the false negative rate, which is how often we miss a real positive. So essentially, the goal, the main idea is that the threshold that we discussed earlier is a key factor in determining like a trade-off between these two metrics. right? The amount of false positives our model makes and the amount of false negatives we make can kind of be traded off by tweaking this threshold parameter. Uh, so so lowering like the FPR would increase the threshold FNR and vice versa. So there's a point at which both these values become equal, which would occur at a particular threshold. And that is called EER, which is equal error rate. And that is what you're being evaluated on in this assignment, right? So the main goal is that you're treating false positives and false negatives as equally costly mistakes, and you're trying to find the best threshold, predictive threshold, at which both types of errors are balanced, right? It is a common metric that is used in face verification. So a lower EER typically means a better model, right? So now that we know, so the EER is essentially what we are being evaluated on. So here's some like general tips about going about the assignment, right? So our general goal is to learn useful discriminative representations like efficiently and in a stable manner, right? So first things first, this assignment has a lot of moving components. We have different data sets. We have different task objectives. We have different loss functions. You will be exposed to like diverse array of like models while you're doing your research. So it's important to first verify that your pipeline works well. And a great way to do this would be to just grabbing like a small subset of data and then just iterating through, taking a basic CNN model and iterating through like your entire pipeline to see like everything works as expected. Like you're not raising any errors at weird spots. Your runtime is not crashing because of silly issues. Because once you start scaling things up and adding complexities, it'll become much harder to detect those errors. And then things can also crash. Like you might have like a run that you started like at the middle of the night, as CMU students usually do, and then you wake up to a runtime error, which could have been avoided, right? So debug your losses, shapes, and labels before with like a small subset of the data before starting your full training. And then the more important thing to take into consideration is to always be mindful of the actual thing you're being evaluated on here. So in the assignment, we expose you to like these two tasks, right? We expose you to this classification task and this verification task, which will be talked about more later. So but essentially, on a high level, you can see it as we tell you to train like this. So the way it works on a high level is that you have this model that outputs an embedding, which is a high dimensional vector that is a representation of your face, right? And then you apply some transform on this. We'll call it the classifier head to now project this embedding into into another space that is hopefully like separable and is like segregated into these nice regions, and then you can associate a label to this space, right? That is the objective of classification, to hopefully create like these separable regions, and which will then make it easier to classify, right? Now, inherently, that somewhat makes your embeddings discriminative, right? But that is not the primary objective of classification. Points only need to be on the correct side. So if you see the picture right there in the separable feature section, points only need to be on the correct side of the correct side of the boundary, right? On the correct side of the decision boundary. There's no explicit pressure to have these points be clustered together as well. So, but your actual task that we're evaluating you on is on the discriminability of the embeddings, right? So let's say I was comparing let's say I was comparing the image you see. This is one image, And this is the image of me, and this is the image of Mengchun, and this is another image of me. And let's say our threshold is like some value that is greater than the distance between these two, right? So in this situation, even though we belong to the to different, even though me and Mengchun are correctly classified into different classes, in the interest of verification, we get lumped together to be the same face because we are closer together in the in this multidimensional space than a picture of me and this other picture of me, which might have been taken in like a different angle, right? So that's why we introduced this concept of verification loss, where the goal, well, where so we introduced this concept of verification loss, where there is explicit like pressure to ensure that all my images kind of cluster close together as well, so there is no ambiguity in when it comes to like measuring my face versus let's say Mengchun's, right? And you'll understand more of this while you go through the assignment. But the main key takeaway is that never forget what you're explicitly optimizing for, what you're explicitly being evaluated for in this assignment. So what you're optimizing for will be changed. You might optimize at the beginning for classification in hopes of it giving you good verification performance. You might explicitly optimize for verification, and you'll see that that is often like hard to optimize for. You might optimize a weighted combination of the two in hopes of like converging better and things like that. But essentially, the main takeaway is that never to forget like what it is that you're actually being evaluated for. And again, another thing to consider is that when you're using these different losses, these losses might have like different scale factors associated to them. So like a 2.0 classification loss might mean something very different than like a 30.0 verification loss, right? So it's also important to like do your model selection based on things like EER and verification accuracy rather than the raw loss values. You can also make some healthy default choices, like Atom and Atom W are generally strong default optimizers. If a loss starts exploding, always a good idea to lower the learning rate, as you might have also experienced in homework 1P2. Again, reproducibility matters. We with augmentation, dropout, some other techniques we'll also be introducing like drop block. There's so much like randomness in our pipelines that it's important to like set seeds to everything so that we can reproduce our experiments, right? And are reducing the variability among similar configurations. And it's also important to like log all your configurations and log all, even if possible, even your runtime states, so that you can debug why a certain run went like bad, right? Again, small changes can shift Kaggle scores a lot. Common pitfalls could be like, yeah, training looks fine, like you're getting good classification performance, but your embeddings are not useless, but they're not as good as they can be, right? Because the verification is not something that you also explicitly optimized for. Uh, Augmentation plays a big role in this assignment because you can increase the variability in your data, but also over augmenting. Some augmentations are better than others, and over augmenting can also just kill any learning signal, right? For example, let's say you completely mask the entire face. It's not going to do much. There's no signal to learn from. And common mistakes to take care of, which hopefully you can rule out while doing your small subset tests, is to like forgetting like your train, your eval mode switches, and so on and so forth. All right. Again, this pretty much goes back to the
Sorry, Drew.
yeah, what's up?
There's a question from students here.
Oh, sorry, yeah. How can I answer it? What's the question?
I was wondering, in the previous slide, why does metric learning lead to more discriminative features?
Can somebody, couldn't hear that very well. Could somebody?
Mm,
Oh yeah, why does metric learning learning lead to more distributed features?
Oh, so is that question? Why does metric learning lead to more discriminative features?
Yeah.
So metric learning explicitly. So you're explicitly trying to minimize. So when you get to metric learning, there'll be things like triplet loss or n pair loss, where you're trying to explicitly minimize the distance between uh, uh, pairs of objects or triplets of objects that belong to the same class, and expand the distance between objects that belong to different classes, right? So that is what leads to what potentially increases the discriminative abilities. So we are explicitly trying to minimize intra-class distance, and explicitly trying to maximize interclass distance. And this is not an explicit objective for classification, which is why metric classes are could be like more better suited to create discriminative features. Does that make sense?
Yeah, that makes sense. And I was also wondering, you mentioned how like different losses might mean differently because your values could be very different. But like aren't like why can't we just normalize the losses so that they span the same range of values?
You could normalize the losses, but then so there's something like where cross entropy would essentially be like what is it called? So that's one of the things I was talking about, where you'd have to when we're doing multi-objective things, like let's say you're optimizing for classification loss and you're optimizing for verification loss. Now classification loss will probably start at like 5 or 6, and then verification loss would start at like 30, right? So when you're jointly optimizing these two things, they're in different scales. So your model would like explicitly try to like optimize verification first, and classification will be pretty bad. And then until like the scaling starts like stabilizing, only then you will get like equal optimizations on both ends. So you would like try to like add like some sort of like a normalizing factor to like the classification, maybe like 0.1 or 0.01, to like ensure like those losses are normalized, and you're optimizing the way you want to, right? If that makes sense. Does that make sense?
Wait, we're getting trace data for verification. I thought there was only test and validation for verification.
Sorry, could you repeat that again?
I didn't realize that we were given training data for verification. I thought like we were only given validation and test data for verification, and we're only training the model when we're doing
You're
class.
given training data for classification, but you can use that training data for optimize verification, right? So that's how these metric losses work. So you're given verification data to evaluate on, but you can use the training data. You can use the image label triplet, like image label pairs, to construct your optimizing objectives in a manner to optimize for verification, which is what N will be actually covering like right after my section.
Thank you.
Cool. Any other questions? Okay, I'm gonna move on for now. All right. So yeah, just like I brought right now, loss might be something important to monitor, but again, be careful with how you monitor this, because the scales might be different, and in different contexts they might mean different things. Because for one run, let's say you used a joint um, a multi-objective loss function, and for the other run, you purely used classification loss. Those two runs are not directly comparable via their loss values, right? You would use something as your EER, how the model performed on EER, to make that determination, right? Now, classification accuracy, like as we discussed earlier, you're not explicitly optimizing for distances. So you could get a pretty decent verification performance with classification, just by purely optimizing for classification. But that might not be enough. Like you might need to like fine tune a little bit with verification to like push your model little bit further to like get to those high cutoff scores. Um, Yeah, again, this is not something that we have natively set up, but it is pretty straightforward to set up. Is something that you could monitor is the mean intra-class distance versus the mean inter-class distance of your embeddings, and that might be also indicative of how your of the discriminative capabilities of your model, right? Practical advice as usual, you plot your metrics every epoch. We have this natively set up, I believe, via 1DB. You might be tempted to turn off your logs. Don't do that if you can afford not to. And then also try to checkpoint as much as possible because you don't want to miss out on your golden egg. Watch out for validation noise, common things. So common pitfalls again, because of like the multi objective nature of our task. Please try not to pick checkpoints based on training loss. Um, you All of these are over optimizing on a single metric blindly might also be pretty bad. Actually, one thing I will recommend is this is a pretty well researched field of like the face verifications, and there's a lot of face verification benchmarks that you can refer to online to kind of get like a hint on like what models would be good for this task. But just keep in mind that we have the requirement that you actually implement any model that you see, and then things like attention and LSTMs and RNNs are not allowed, and you might be just that you might be asked to prove how you implemented things, right? But besides that, this field is pretty well studied. I would highly encourage people to refer to benchmarks. Like there's a lot of popular benchmarks for this task, and people have many creative approaches to this task. So I would highly encourage you to see these benchmarks and see how this task was approached. Um, this is a very interesting thing that happens with this homework in particular. So in your previous homeworks, you might see this big gap between the training accuracy and the validation accuracy, and you'll chalk it up to this being like a common instance of overfitting, and you will give up on your model, right? But something strange, really weird, that happens in for this task in particular is that. You'll see for certain models, you'll see the training accuracy reach 100% pretty quickly, while validation accuracy is pretty low, like 0.0, even 1%, 5%, right? And out of nowhere, in like the 20th epoch, it suddenly shoots up to like 80%, 90%, 100, like even 95%, right? So there's a name for this. It's called, you can read up on it. It's called grokking or delayed generalization. I have no idea why it happens, but it does tend to happen. Basically, the main concept is that the models just may suddenly generalize after long plateaus. So our main advice to you would be to treat this homework a little bit differently as you have done in homework 1P2. Train until the validation metric stops improving. I know this is not, it doesn't sound great, right? Because you do want that instant validation. Runs can be long. You do want to make you want to make quick decisions so that you can quickly discard candidate and move on to the next. But that process of decision might not be that quick for this assignment in particular. So we recommend you to just train until the validation metric stops improving, or just use the fixed LR schedule, like assign annealing and set it up for like 50 epochs and just let it run in the background while moving on to a different model. Basically, don't panic over early plateaus and temporary gaps or mismatches between the train and validation sets, validation performance on the negative side. Right. And here's some techniques you can follow to tackle overfitting. Right. You can do something called label smoothing, stochastic depth, stochastic depth drop block. These are essentially, so you'll be training a lot of like deep neural networks in this assignment. So essentially, stochastic depth and drop blocks are like regularization strategies where you like skip intermediate layers and skip intermediate blocks even. So essentially, just to like create more robustness in your model, right, and not be too dependent or like to not have too much pressure on like your earlier layers or like lower layers to kind of separate the work evenly. And you can use like dropout and things like that. Data augmentation plays a strong role in this assignment. And we have this paper for reference. It's linked here, the bag of tricks for image classification with CNNs that might be useful. There's also this a thing called test time augmentation, where you augment, which is kind of seems counterintuitive, but for some reason works. I will let you look that up on your end. But essentially, it's like creating a different setting during during the inference time than what was in the training time. And for some reason, well, there's a reason why. There's a hypothesis of a reason, but for some reason, it just works well in this task. All right, that is it for me. Any questions I can answer?
Thank you, Pru.
Okay, cool. Thank you, Anne.
Um,
Oh, I have to stop sharing.
okay. So is it like shared in also? So how I'm going to talk about the loss function. So as other TA has mentioned before, so here in this homework we have two tasks. First one is the classification. So for the face classification, the goal is to very straightforward. So you are given an image and you are going to predict which identity it is belongs to. So each person is treated as a class, and we usually assume that the identities seen at test time were also present during the training. But for our face verification, it is different. So here we are given two images, and the question is, you need to predict whether they belong to the same person. So importantly, the identity we see at the test time may never appear during the training. So this makes the verification an open set problem. So the key part here is instead of memorizing the identity, we are learning a way to measure the similarity between the faces. So to visualize the difference in the classification, we only care about the predict the correct label. So as shown on the left picture shown here. So as long as the correct class has the highest score, the loss is satisfied. But in contrast, a verification, we care more about the discriminative features. So the question is, are the faces of the same person are close together, or are faces of different people are well separated? So this difference means we need to think about the loss function we are going to use. So in classification, we usually use a standard classification loss, which encourage sample of the same class to be grouped together and separated from the other classes. However, these losses do not explicitly control the geometry of the feature space. So I thought you should be familiar with the cross entropy loss. It is commonly used in classification loss, but it doesn't so good to enforce the geometric constraints. So as shown in the visualization of the cross entropy here, so you can see the two samples can be correctly classified, but they are still being very far apart in the embedding space, like the F2 and F3 here, even they are classified as the same class, but they are still very far away from each other. So the thing is, so what we are going to use from what do we want from a good feature representation for verification? So here we want a larger intra-class similarity. That means the intra-class distance is smaller. And if two images have a smaller inter-class similarity, so it means it has a larger distance between each other. So the main goal here is we want the features of the same class have larger similarities, which means a smaller distance than the other classes. So this leads to the concept of the discriminative features. So for the face verification, we want the embedding such that faces of the same person have smaller distance, while the faces from different people have a larger distance. So visually, so this corresponding to a tight intra-class clusters with larger interclass margins. So in this setting, the geometry of the embedding space matters more than the class logics. So to achieve this goal, so we have given two paradigms. You can look more, search more about this. So the first one is the magic learning and the pairwise learning. So it directly trains the network to control the distance between the embeddings. So here, the second one, I will talk about this later, but the second one is a margin-based softmax. So it normalizes the feature, factor, and class weights, and it uses cosine similarity instead of dot products. And it add an explicit margin between the classes. So actually, for the homework, two-part two homework, I would suggest to take more look at the margin-based softmax. So, okay, so let's talk about the first part, the magic learning pairwise learning. So, so here, as I mentioned before, so it directly changes the network to control the distance between the two embeddings. So some example of the magic learning losses as shown here. You can take a look at the center loss, triplet loss, like n pair loss and contrastive loss. So this is loss you can take a look, but I would suggest you more pay attention to the margin-based softmax, so which is modify the standard softmax loss by normalizing both the feature factors and the class weights. So using the cosine similarity instead of dot products. So I would suggest you take another look about this loss function, and maybe you can implement in your not like in homework. So like the sphere phase and arc phase or combined margin phase. So these are the ones you may take a look. So how to get started? So it's a kind of a summarize of the what we are talking about. So first you can use a simple network and cross entropy loss for your early submission deadline. But if you want to achieve a better performance, you can use better architecture. And you can also try the data augmentation, like different kinds of augmentation. And also you need to try different kinds of loss function. And I would suggest you take another look at the YouTube, like the recitation videos we have uploaded in the YouTube, the 20 and 21. And also you can take a look at this website about the metric learning. And we are going to talk about like the homework workflow, like you can also use different approaches. The first one is the joint loss optimization, like you combine the cross entropy and contractility loss from two tasks. Another one is the subsequent sequential, like you do the classification first and then do the verification. Maybe use different kinds of loss function. So here comes to our question part. If is any question about the whole two-part two?
What's the difference between dot product and cosine similarity?
Sorry?
What's the difference between like measuring the differences of two features with the dot product versus measuring the two differences with cosine?
I think that one you should take a look at like the cross entropy, like it's like equation, how it is implemented. Another one is like for the margin-based softmax, you can take another look and how they calculate this loss. Like you can take a look at the papers, like how the equation are established. Yeah.
Hey, did somebody say difference between dot product, cross product, and
Oh,
cosine
yes,
similarity?
the difference between the dot product and also cosine similarity.
Wait, so dot product, the magnitude also plays a factor, right? But cosine similarity is normalized by the magnitude. So things that are aligned on the same direction are one, that belong to opposite direction are zero, and things that are orthogonal that belong to opposite direction are minus one, and things that are orthogonal are zero. So essentially, it's a dot product but normalized by the
Oh,
magnitude.
why would we want to use something like cosine similarity versus something that minimizes or maximizes like distance? Because that seems a lot more powerful.
So we, as a convention, are using cosine similarity for as our like verification in our verification metric, right? You could have used any other distance-based metric. We just as a convention are using cosine similarity, so it is in your best interest to optimize for cosine similarity. Does that answer the question?
Yeah.
Cool. Thank you.
Uh, for two part of it is over, but we have another session about the instruction about PSC. Yeah. So should we have a break for that or because the pizza has arrived? Thank you, Peru.
No worries.
Hello. So today I'm going to introduce the PS user policy to you guys. And first of all, for all homework P2s, do not download datasets yourself, and also the environment. We have already provided them to you in the PSC. Also, for example, if you want to store any files in the PSC, make sure that you store them in your own Jet directory, which I will introduce you later. Also, students will only need to use V100 for all homework part 2s. So first of all, what is the Jet directory? Jet directory is Jet home and your PSC username. This is your personal folder. Each user have 25 gigabytes quota in total. It should always be your default directory when running the notebooks and storing all the outputs. Also, we have Ocean directory. Ocean directory is shared among the whole project. It is TA prepare shared environments and shared datasets inside the Ocean directory. Also, we have a local directory. The local directory is when you request for a node and its storage. This is temporary local storage, only allocated to GPU node. It only exists during the job and is cleared when job finished. Also, you can also there for your project for 1170 785 or 685, you cannot use our homework allocation in PSC for you to do your project. However, you need to apply for your own PSC allocation for your project work, and it is detailed to do that is also in our Piazza post and the recitation zeros. You can check that. For doing the projects, you can also use the AWS or Colab Pro as a computation resource. And there's a Piazza post about PSC user guide, and all the posts about PSC, you can check that in Piazza. It is post note 70. And now let's have a demo using VS Code to connect to PSC. First of all, you need to download the SSH extension. Is after downloading the remote SSH extension, you can Okay. So you need to download the remote SSH extension. After that, you can Okay, okay. After that, you can go to the Remote Explorer and click the plus sign in the SSH here and SSH your PSC username, which might not be the same as your access ID. So the PSC team will send you an email about your PSC ID, and you can change your password in the link they provided for you. Now you can enter your password. Press the Explorer and select Open Folder here, and this is your Jet directory. And okay. Typically in our homework part 2s, we will provide you step-by-step guide to how to use PSC when you're doing your homework. So this is how you request a compute node. Interact, GPU shared. See here is the time for a interact section. So now the PSC is trying to give us a resource now. Now it says no, V11 is ready for the job. To load the Anaconda module, you type module load Anaconda 3. And after that, you can type conda activate to activate the corresponding environment for your for you.
Could you enlarge the screen? That's very hard to see. Oh. in the text.
Command plus.
Okay. Don't worry. So this type of the command is provided in our homework to P2 notebook. After the environment is ready, we can go to the Jupyter notebook. Use this to start a notebook server. And you can copy and paste one of these URLs here to select kernel. First, you need to install the extension here. And after that, you can get data from our shared path, and this also will be provided in our homework P2 notebook. And that's all for my part.